Hi, everybody, and welcome to a special briefing for the 2019 RASC-AL Special Edition Moon to Mars Ice and Prospecting Challenge. I'm Stacey Dees, Outreach Manager for the National Institute of Aerospace, and as a part of that role, I am really privileged and honored to serve as the RASC-AL Program Manager. Today's briefing is really a critical component of the challenge. We use it as an opportunity to share really valuable lessons learned. We want to use this as a way to increase your success, your capabilities, kind of sharing what's happened over some of the previous iterations of the challenge. It's our way of building on the collaborative successes and sharing in the collective knowledge of these really important, critical ISRU and prospecting capabilities. Before we introduce today's presenters, I'd like to make a few other introductions from your RASC-AL program team. Joining us from Hampton, Virginia at the National Institute of Aerospace is Victoria O'Leary, who's our program coordinator, and Ania Cotton, our program assistant. Hi, ladies.
Hi. Hi.
Joining us from NASA headquarters in Washington, D.C. are presenters Rick Davis and Bob Cullum. Rick currently serves as the Assistant Director for Science and Exploration, conducting extensive integration work between NASA's Science Mission Directorate and the Human Exploration and Operations Mission Directorate on deep space policy, including Mars exploration policy. Rick also co-leads a joint study to identify potential human landing sites on Mars using current assets, as well as to define future reconnaissance needs required to support human surface operations on the Red Planet. From the first year of this challenge, Rick has served as our #1 champion and sponsor. Hi, Rick.
Hey.
Bob is a program coordinator for NASA's Science Mission Directorate in Washington, D.C., and he was an integral part of the 2018 Mars Ice Challenge. At the end of last year's challenge, Rick and Bob actually sat down with the teams who participated in the challenge and co-hosted a knowledge capture session with them. The information that they captured during that session serves as the foundation for their presentation today. Hey, Bob.
Hello.
Our third and final presenter joins us from the NASA Johnson Space Center in Houston, Texas. Dr. Stephen Hoffman is an engineering specialist with the Aerospace Corporation who has extensive experience designing and implementing field tests of potential systems and operations for future human exploration of the Moon and Mars in analog environments. He has an incredibly diverse background that includes deployments to both the desert and the Arctic. Hi, Steve.
Hello.
So we're getting ready to jump into the meat of the presentation, and I really want to encourage everyone that you are welcome to, at any point, use the live chat feature of the YouTube page to ask a question of our presenters, and we'll make sure to answer them during the stream. So with that, let's jump right in. Over to you, Rick and Bob.
Okay, thank you, Stacey. And we're going to show the presentation. So in the presentation, we're going to show you some pictures. Was one of my favorite ones. It's a panoramic view. Hang on, we'll get it up next page. It's a panoramic view by the rover Curiosity, and I love this because a lot of times when you look at this, it makes it feel like you're in an Arizona desert or on the Atacama Desert down in South America. And so we have to be careful about those kind of comparisons. You know, humans do that naturally, but it's really, going to Mars is a lot more like going up Mount Everest or K2, which is the picture you're seeing here. And the point being is it's hard. It's actually probably 1,000 times, if not 10,000 times harder than scaling one of those major mountains. And it is crucial to do your homework. And the challenge that you all are becoming involved in is actually probing in an area that is really critical for knowledge that we're trying to get to enable getting to Mars. Next slide, please. Stacey mentioned, I co-lead the NASA Mars Human Landing Site Study. And basically, this has begun the process of picking out where we will have a base on Mars. And we're doing it now because it takes so long to get missions out to Mars that we have to sort of start that process so that we can use our assets that are there and then figure out what our future assets need to be to actually really pick a good location. And when we did the first workshop, one of the major findings was that water and access to water probably drives base location. And so over the last 2.5 years since we had that workshop, we have actually really focused on finding the water and understanding what it takes to produce from it. And so if you go to the next slide, there's basically two broad categories of what we would call water feedstocks at Mars. There's subsurface ice, which this competition is probing into, and there's what we call hydrated minerals. And so hydrated minerals are basically water molecules locked up in, if you will, rocks or granular materials, such as dirt, if you will, or regolith, as we call it. And so that one's tricky because figuring out where those fields are from orbit is has its challenges, and then understanding the nature's there. Subsurface ice also has its challenges from figuring out where it is, but we know there are significant ice fields at Mars, particularly up in the northern hemisphere. If you go to the next, Bob, over there, thanks, Bob. There's actually really 4 major questions that need to be asked about water. And number one, is it really there? So as I alluded to, for example, when you are using a mass spectrometer from on orbit and you get a hit that there's a type of material that has water molecules in it, you don't know whether it's a vein or whether it's spread all across the surface. It's just triggered that spectrometer to see it. And then what we have to do is go do ground truthing, which is like sending a rover to try to find it. And we've had challenges doing that. That's an example of, is it really there? Second question is, can you produce it economically? And that's really what this ice challenge is helping us probe. And so really it rotates on 3 questions. What is the mass of the equipment you have to send to produce it? What is the power levels you need to have? And 3, what is the operational complexity of assessing it? For hydrated minerals, NASA has done a lot of work on that because they exist in other places. But for Mars, we didn't realize there were these buried ice sheets for literally until about 10 years ago. And so the technology development is not where we would like it to be ideally. And so you all are bringing new perspectives that actually will help us figure out how to access those and to essentially start converging our understanding of that mass, power, and operational complexity question for this, can you produce it economically? There are 2 other questions, which I'll just mention to round it out, is how much water are we really talking about? So if you're talking initial missions, it may not be much, but if you move toward more sustained presence with growing numbers of people, like what we have on the space station, or you can even take a more aggressive presence, such as what's envisioned in some of the SpaceX work right now, that's a lot of water. And a big chunk of it at first is just used for fueling the Mars ascent vehicle for your ride home. But the key point there is you need to know how much you're talking about. And then finally, ice is an interesting one because it actually has geographical dependencies. It tends to be further to the north, and you need to make sure that the Mars ascent vehicle can get off of that kind of a location and rendezvous with the mothership that comes home. And so those are the big 4, and we're working on those all things, but this ice challenge is really helping us try to understand number 2. And then what we're going to be presenting are lessons learned from last year's ice challenge, but and this is a little different than some competitions because we are really trying to build on each year's work. We're going to count on you for your lessons learned too to help inform the following year's team when we do this, because it's only by building on the shoulders of giants, and I don't say that lightly, that we're actually going to figure out all the ideas that we need to really go chase these options down for enabling human spaceflight to the surface of Mars. That's it.
All right, Steve, I think you're tackling the first couple slides for the lessons learned.
Sure. So, okay, there we go. Accessing the ice. These questions, or answers to these questions, were gathered from the teams over the last couple of years. So, I'll try and channel the teams that were provided us this information to give you some idea of what they found that, based on their experience, what they found that worked well or didn't work, and you can take that into account as you choose when you're designing and building your system for this coming year's competition. In this case, accessing the ice. Remember, what you have here, or what you're going to be faced with, is a block of ice that's buried by, this year, several layers of regolith material and different types of material that you'll have to somehow get through to get to the ice before you can start with withdrawing water or ice, as you choose, to actually produce the water that we're seeking. Some of the comments that we received was it would be nice to know what the material was that they had to drill through before they drilled through it. And you'll see that in a number of these, the pages here, this one in particular. But if you think about the problem that we are faced with, we being NASA and the other organizations that are looking at how to solve this problem, we won't know what that layer of material looks like. We'll have some general idea of what its, say, bulk density is. We may have an idea of what some of the bigger chunks look like or where they are, but we don't know what they are, and we don't know necessarily where all of them are. So this is a challenge that everybody will be faced with, and we're looking for ideas from you for how you would instrument your device, and how you would to tell you what kind of material you're interfacing with, and how you would build a device that's robust enough to get through these different kinds of material. We can't ensure that we'll come up with a place that's nothing but dry sand and therefore very easy to get through. It's probably going to be a combination of things. And part of the challenge for this year is to be faced with a number of different layers and have you tell us, or have you tell your machine, how you're going to drill through all those different layers. The words that are in green on the right-hand side of this chart are taken from the guidelines or the competition rules for this year. So there are a number of layers that you'll have to drill through. We're not going to tell you how many, and we're not going to tell you in what order they're going to occur in, but they're going to be taken from this list, and it's up to you to figure out how to drill through them and reach the ice that's below all of them. Some of the things that
we actually you.
Go ahead.
The question was, can we use a power outlet, or must our system be run by batteries?
Steve, you're muted.
Is that better?
Yep, we can hear you.
Okay, thank you. I'm not sure how I got muted, but I'll look for that in the future. No, well, every station will have access to power, but from an outlet. So you'll have 110 volt power outlet, common household power outlet that you can draw from. You'll be limited to the amount of watts that you can put into your system. So if, and I don't remember that number off the top of my head, but you don't have unlimited power. But you do have power from an outlet. You don't have to provide batteries to make this work. Unless you choose to do that, you're not prohibited from using batteries, but you don't have to rely on batteries as your sole source of power. Let's see, I'm looking at some of the other items on this page. A number of teams found that that when they tried building their own version of the test station with a block of ice covered by some sort of regolith, one of the surprises that they found when they got to the actual competition was that the material that was covering the ice was damper than they thought. It had more water content than they did in their testing. And a consequence of that was that they, their devices that were trying to get through the regolith layer tended to clog with mud as they were drilling through them. You can, depending upon what device you use, that clay material, and that's one of the options, or one of the types of regolith that's in this list of options for this year, can become very sticky, and it can stick to whatever device that you are trying to use to remove that debris layer. One of the things that the teams found that did work was to have some kind of device, a brush or a something that they could use, that they could scrape this material off of their, in the example that I'm remembering is an auger that got clogged with a bunch of sticky debris, and they had a brush on the side of their drilling rig that they could use to then unclog their auger and put it back into their drill hole and continue drilling. So just be aware that the kinds of materials, that the device you use to remove the regolith can get clogged with these kinds of materials, and having some way to remove that material could be useful in as part of your design. One team used a percussive, well, several teams, I guess, used percussive drills. They found that these worked quite well in getting through both the debris layer and actually drilling into the ice. Not all the teams used them, and the teams that did not use them also found successful ways to get through the debris and get through the ice. So it's not a universal means, or the only means of getting through the debris layer, but several teams found that it worked quite well for them. So you might keep that in mind. Let's see, the other points that are made on here, I think I've covered in one form or another. So let me pause there before going to the next page and ask if there are any questions that that the people online might have.
I do. Yeah, Steve, one comment I would say, this is Rick, one thing I might add is that the regolith this year, or two comments, regolith this last year actually had too much water content in it. That's probably not realistic for Mars or Moon, and so this year it's a different type, but it's those mixed layers, and I don't know if you specifically mentioned that. But another key point is that this problem that Steve that you alluded to, which is that you don't really know what we're going to be drilling into. We're going to have very little ground truthing prior to actually attempting to do these kinds of operations. And so understanding that is really a problem that exists both on the Moon and Mars. And so this year, understanding those torques going down through the regolith is really something we're hoping to learn a lot more from by doing it. And that just to amplify a little bit on Steve on what you were saying.
And one point of clarification on the batteries question that came in. As is stated in the rules, augmenting the system's power supply via batteries, solar power, etc. is not allowed. The only power source you have available to you is what you're plugging into on site. So plan accordingly.
Okay, thanks.
Tori, did you have another question come in?
Yeah, we do have some questions from YouTube.
So, Vicki, before you do that, let me go back to one of Rick's comments. Even though the debris layer that we had last year had more water content than we thought it ought to, that's another area where there's some uncertainty. And some of the profiles that I've seen that people have talked about for covering up ice layers is to have a very dry layer on the top, meaning very little water content in it. But the deeper you go, the closer you get to the ice, there's ice that has infiltrated into the debris layer. So it's something like a piece of concrete. And as you're drilling through it, if you choose to use a drill, the friction that's caused by the drill itself can heat up that ice and turn that debris layer that was very hard and not very damp into something that is damp. So there is a way that given some of the, even though we're uncertain about it, we don't know what that vertical profile looks like, there are ways of creating mud on Mars that could cause this kind of problem to occur. So I just want to throw that one in.
I suppose something else on that point, because teams did have to deal with mud last year. The teams that were able to tackle it most effectively were probably the teams that were moving the least of it, the ones that had the percussive drills that were not trying to lift it out, and the smaller bits were, I think a lot of teams got hung up trying to move large volumes of heavy mud and dirt with bigger augers. And I think the results would suggest that, especially when dealing with the mud, that wasn't the best strategy.
Well, and we have to be mindful that on Mars there is an atmosphere, but it is a very low pressure. So it's essentially like having a vacuum on top. So you're actually trying to protect the ice with the regolith layer. So the minimum amount that you disturb it, this would apply on the moon even more so, assuming they're pretty solid ice deposits. Because you're essentially using that overburden layer, if you will, to act as an insulator away from the vacuum. And so that's a key point that I think we've collectively all begun to realize.
Right, not as big of a problem on Earth, but you don't want all your ice sublimating away while you're drilling it. Yeah. Tori, over to you for questions.
Hi. Some of them can be addressed actually by reading the competition basics page. I posted a link in the chat. One question we did receive is, could we control the system wirelessly, and can we collect data wirelessly?
Steve, do you know the answer to that one?
I'm going to let Stacy answer that one. I think she knows the what's in the rules this year better than I do.
Hey there, everybody. Yes, actually, I'm going to read you exactly what the guidelines say about that. There will be no local Wi-Fi access available to the teams for the competition, but teams may implement a direct, localized wireless connection between their water extraction and prototype system and computer control system, but they must accept the risk of possible interference.
Thank you, Stacy. Any other questions, Tori?
I think we're good. We can keep going.
All right, Steve, we'll move on to the next slide.
All right, we're on motors now, is that correct?
Yes, sir.
Okay. Many teams in the past couple of years have tried using a system to drill through the regolith and get into the ice. Some of those drills have been just straight rotary drills. Some of them have been percussive drills. These have, some of them worked well, some of them did not. As Bob pointed out, some of them were connected to rather large augers, which were several inches in diameter kind of augers that tended to be challenged by the amount of this clay material that they had to lift. But one of the, so that that's a separate issue. I think we talk about augers a little bit later on. But with regard to motors, many of the teams went down to the local Home Depot or Lowe's or your favorite hardware store and bought some off-the-shelf hand drills, and then proceeded to disassemble them to get down to the pieces that they wanted to use. One of the things that they were challenged by in taking this course of action was that they didn't have a lot of information about what the motor inside needed in terms of the input power. or what some of the other characteristics that they would need to control a motor were not available with something that you can buy off the shelf. Another problem that they found was that a lot of the motors that, while they're good for home projects and small or short time usage, a lot of these motors were challenged by trying to develop either the torque or operating for the time periods that this competition is going to require. And they had many of the motors overheated, some of them burned out. So you need to be mindful of that if you're going to have some kind of device that relies on a motor, electric motor of some sort. The teams that found or that had better success looked at more industrial or larger scale motors that they could find not necessarily at the local hardware store. One particular brand name that was mentioned was a Grainger. Several of you may be familiar with the Grainger Supply Company that has that its customer base is more of the industrial or construction industry type of usage rather than home usage. They found they had better success with being able to use those motors. They had less problems with overheating. They had, as far as I'm aware, no problems with burnout. So that maybe the way to summarize all of that is trying to find an inexpensive motor is not necessarily the best solution here. The problem you're tackling is challenging for the kinds of equipment, even in this test sort of setup, and trying to come up with an inexpensive drill motor may not work for you in the long run when you start looking at how much torque you have to produce and the periods of time over which you have to produce it. You could be running for, the test periods run up to 6 hours in length. So conceivably you could have one of these motors operating for 6 hours at a stretch without being turned off. That's quite a bit of a challenge in terms of heating for some of these the local hardware store kind of motors. And when you're putting together your test plan, you might consider running whatever motor you pick, and maybe doing this early on in your development stage, running that thing for 6 hours at a time and with some kind of load on it, and see how well it performs, because that's what you'll be faced with during the competition. Also, having some way to monitor whether that motor is overheating or not is another feature that you don't typically find on the kind of hand drills that you can pick up at the local hardware store. Many of the teams would use their fingertips to try and decide whether the motor is running hot or not. Once you start into the competition, you won't be able to touch your test rig anymore. So the fingertip method isn't going to work when you're trying to monitor the temperature of your motor and decide whether you have a problem in that regard or not. So coming up with a way to give yourself some means of monitoring the performance of the motor, whether it's how much amperage is it drawing, or how hot is it getting, or how much torque is it putting out, you need to think about how you're going to do that without having any way to directly touch or interact with that motor once you've started the competition. Integrated testing was also something that was brought up, and as I mentioned, testing this motor for the time durations under some kind of representative load comes under that heading, I think, and the integrated testing in general is something that you need to be mindful of. During the first year of the competition, many of the teams tested the individual pieces of their drilling equipment, and they found that the individual pieces would work well in those kind of settings. But once they had not taken the time to put all the pieces together and try to operate it as it would be operated in the competition itself. And they found that they had problems that would have been uncovered if they'd done an integrated test. So a finding or a recommendation would be to make sure you build into your schedule, your development schedule, a generous amount of time for putting all the pieces together into the configuration that you intend to bring to the competition, and running that integrated system, all the pieces, everything running through all the different configurations or modes that you plan to use it for, and make sure all the pieces work well together in that integrated fashion before you arrive at the Langley Research Center. Let's see, I think, yes, go ahead.
So just to amplify on one thing you're saying is that, you know, an integrated and test environment also means you're actually drilling and into some sort of representative case. So having simulated regoliths and ice, you know, that you're going through, because it is challenging because you're going through different types of materials, and making sure that works before you show up at the competition is really key, so that you really have a sense of how that works. And I would say mistakes of the original teams in the first competition were totally understandable. We've done that in spaceflight a lot of times. But in the end, the one thing we've learned in spaceflight is that you really integrated tests, and that as much as you can get to the actual environment is really the best proof that, or best confidence builder that you're ready to go.
Let me make one more comment here, and then Tori, I'll see what kind of questions we've got. Three-phase motors were used, but the teams that used them found that it put out a lot of RF interference, and that caused a problem with their control electronics. So there are motors that are not three-phase that have the capacity, if you will, in terms of the amount of torque that they'll put out and the loads that they'll take otherwise, that will handle that problem without putting out that sort of interference. I'm sure there are three-phase motors that do not have interference problems, but you should be aware that there are some that do not, and that those can interfere with your other control electronics. So Tori, do we have any questions on this page?
We don't have any questions yet, but I'll let you know when we get any.
Okay, Bob, why don't you go on to the next one then? The water retrieval. There were some very creative ways of getting water out of this block of ice. I won't try and go through all of them, but many of them involved some way of melting the ice in place and then drawing the water out by means of a pump. The teams that took that kind of an approach faced a couple of problems. Pumps, there are some types of pumps that want to have water covering the inlet to the pump before you turn them on. There are other kinds of pumps that don't care. The particular kind that doesn't care is called a peristaltic pump. So as you might imagine, the teams that had the pumps that needed to be covered before they started were challenged when they either they pumped out too much water and they didn't have anything left to pump, or that they turned them on before there was any water in their device to pump out. The peristaltic pumps seem to work well. Any team that used a pump, a lesson that they learned was to have some way to reverse that pump, because no matter how careful you are, there was some amount of debris that got into the ice layer, and that debris can interfere with the operation of your pump. So having some way to reverse the pump and blow the debris out was found to be a very useful feature to have. Also, the tube that they used to with the pump to draw the whatever water they had created out of the ice block, the larger the diameter that they could work with, the more successful they were. Some teams tried to use very small diameter pumps, or I'm sorry, tubes, and that they found that those tended to clog quite easily. There was one team that I recall that was quite successful in initially getting into the ice and pumping water out, but as soon as some of the ice or the mud that was above it started falling into the chamber that they were creating and created muddy water instead of just clear water, and that quickly plugged the small diameter tube that they were using to pump the water out, and that caused them to their system to stop working because they didn't have a way to reverse the flow and clear the clog that they had. You can use filters. That's another way of stopping any sort of debris from getting into your pumping mechanism. But I guess the lesson learned in general is that you should account for the fact that you will likely have debris falling into whatever sort of water pool that you're creating under the debris layer, if that's the method you choose to use. And you should have some way to clear that debris from your whatever mechanism you're using to get the water out of the ice layer and into your the bucket that you're delivering it to. Other teams tried to raise ice chips out and melt them externally to the ice block itself. Those methods worked in some cases. But you'll remember that as you're bringing ice up, you're also coming through that debris layer, and you have the possibility of getting debris mixed in with the ice chips that you're bringing up. So regardless of where you're turning ice into water, you have a chance of having debris getting into the water, and it will become a problem when you try to, wherever the water is, trying to pump that water with debris in it into the external bucket that we're providing for you that will be measuring the amount of water that you're developing from this well. Cameras. Some teams like to use, since they couldn't touch their machinery once it started, they tried to use cameras to get some idea of what was going on below ground or in areas that you couldn't see anymore once their drill rigs started working. It might be worthwhile to consider adding small cameras in different places as part of your instrumentation so that you can get some realistic views of what's going on in places that you can't get to or are not allowed to get to once you're starting to drill and remove water from the ice layer. I think that captures or covers what was talked about on this page. So, Tori, unless there's any questions, we can go on to the next page.
I haven't yet.
One thing I would say is that having worked Space Station and watching the Ice Challenge, I would say cameras can be incredibly powerful for understanding what is going on, but the issues that Steve's talking about are like really important for understanding how you do that in this kind of setting. And any ideas there are could be really good for the overall effort and for helping your team manage any issues that come up during the competition.
Okay, moving on then to hardware. Many teams this past year, more so than as I recall for the first year, took advantage of 3D printing. It wasn't a universal solution to the problem. There were still some parts that were machined or manufactured in let's call them the more traditional methods. But 3D printing was found to be useful for a significant number of the parts that were used in the overall system that was brought to the challenge. I won't claim to be an expert on what's currently available on 3D printing, but I know that there's a couple of different materials. ABS plastic and PLA are two of the types that were used by these teams. They each have their advantages and disadvantages. So if you choose to use a 3D printing approach for some or many of the parts that are in your system, you'll have to make sure that whatever you're using as your raw material will stand up to the environment in which it's going to be used. One team, for example, found that the ABS plastic melted on them when they were operating at high speed. I don't remember what high speed, what RPM or what the speed that they were talking about at which that happened, but that's an example of where ABS didn't work for the in the environment in which they tried to use it. I can also tell you that using the 3D printing helped these teams to do a rapid turnaround in their prototyping. When they had an idea, they were able to quickly make a physical example of what they had in mind and try it out in some limited testing and get some immediate feedback about whether that would work or not. As opposed to having something that, say, had to be machined and therefore they had to line up a machine shop somewhere with a machinist and maybe be in the queue with a bunch of other projects going on at their institution and facing a time delay that they didn't otherwise need to have or didn't have to have with the 3D printing. Many of the teams that used 3D printing also brought a 3D printer with them. So when something did break during the competition, they were able to manufacture another one and replace it in whatever amount of time it took their 3D printer to create it. The 3D printers that I saw tended to be rather small, so we're not talking about rather large parts or either from a mass or volumetric point of view, but there were some parts that they did need, and they were able to recreate them with their 3D printer and keep on going where they might not otherwise have been able to do that if it was something unique to their device and they didn't bring any spare parts with them. The teams did bring significant numbers of spare parts and tools with them because things tended to break, and you should assume that they will break or fail once you get to the competition itself. So as you're working through your designs, you should keep in mind or think about those pieces of your design that could fail and how they could fail during the challenge itself, and consider bringing spares of those components with you so that you can change them out and keep going on the competition rather than being out of the competition once a critical part failed. The motors we talked about earlier are an example of that. The teams that had some of their Home Depot type hand drills, the motors fail on them. They didn't have spare parts for those, or they didn't have spare drills. Some of those teams went out to the local Home Depot and tried to buy another one to replace it. But if you're thinking about that as you're working through your design, you can start accounting for the critical parts that you recognize that if it fails, your whole system is going to fail, and therefore consider ahead of time having the spares with you so that you don't lose any time rushing out to the local Home Depot or other supplier of whatever variety it is to get the replacement parts that you're going to need. Let's see, I think that covers most of what's on this page. So Tori, are there any questions that came up with this discussion?
We haven't received any questions yet, but I'll let you know what to do.
Okay, Bob, you want to go on to the next page? Let's see. This has kind of got two topics in one, both autonomy and augers. Part of the competition is to run in a fully autonomous mode. The actual situation we'll be faced with on Mars is that in all likelihood there won't be a driller standing next to this device that's able to interact with it in real time. So we're going to have some way of having the machine itself be smart enough about drilling or otherwise accessing the ice layer, and then getting the ice, turning the ice into water and delivering it to the storage device. So there's going to be a trade-off in this competition. We can't ask you to necessarily automate everything with every possible failure mode included. So you'll have to be judicious in picking out how much automation to put into your system. It certainly has to be enough to handle the part of the competition where it's completely hands off, and there are, as the rules are set up, there are more points associated with that, the ability to do that, versus teleoperating these devices. Let's see, that covers the autonomy, I think, although, well, at the bottom of the page, MATLAB versus Arduino. I think I'm saying that correctly. There's a trade-off there in how sophisticated you want to be and how much time and effort you want to put into developing the software to drive your system with those types of automation. So keep that in mind. As I recall, both were used or have been used by teams in the last 2 years. So you'll have to give some consideration to what you're comfortable with, what you're capable of dealing with as far as your team members are concerned when you're building up the automated portions of your system. The augers. Mentioned earlier, some teams used augers that you can buy at the local hardware store. Some of them are used to drill holes in the ground for setting fence posts, for example, or something of that nature. They found that while these worked, some of them were challenged by the fact that there was a lot of mud, and that mud tended to clog up the races on the augers themselves, and they had to have some way of cleaning that off. So some teams use percussive drills, but they had no rotating drilling portion of it. They used a percussive drill to hammer a probe in through the debris layer and into the ice, and at least one team that I recall that used that approach was successful in doing so. So having some kind of rotating machinery is not necessarily the only solution, but if you choose to use it, you should be testing that whatever kind of device you use in representative material that we've told you about, that will constitute the debris layer and the ice layer, to make sure that whatever kind of rotating device you have is up to the challenge of getting through both the debris and the ice. There's one bullet point on here that I did want to touch on in particular, and that's speed and pitch on these rotating devices. As I mentioned earlier, you can high-speed rotation can put a lot of friction into the system, and while that could be good for drilling through something that's very hard, it's also good for melting ice. And once you start melting that ice and it gets mixed in with the debris layer, if you're still in contact with that debris layer, you can start mixing the friction-generated water with your debris layer and creating mud that otherwise might not be there. So you need to think about how fast you want to turn some of this rotating machinery with those kind of issues in mind. The pitch that you put onto this rotating machinery will also starts to become a factor in how much how much torque you have to put into the rotating machinery, and also the speed in order to lift, get that auger to lift debris and perhaps even ice chips, if that's your approach, out of the hole into some above the debris layer where you can do something with them. Some teams used a casing, a tube that they put around their rotating device to keep the debris layer from falling back into the hole, to keep the debris out of the hole once they're operating in the ice layer. That's an added complication, it's added mass for your overall system, but it has the benefit of keeping the debris layer in large part separated from your rotating machinery, and when you're drilling through the bottom layers or the deeper layers of the regolith, and certainly once you get into the ice layer itself. So it's a consideration. There are teams that use them. There are teams that did not. Both were, some succeeded in both cases, some did not succeed in both cases. So if you choose to use that approach, be sure to include it as part of your testing phase to make sure that the concept that you're trying to implement works in the real world and not just on paper. Let's see, I think I've covered what I wanted to cover on that one. So, Tori, if there are no questions, I think the next page is something that I'll turn over to Bob to handle.
We actually do have a question from the chat. It says, have any teams in the past been able to gauge the efficacy of integrating a heating element within their auger or drill?
Yes, they did. And in some cases it worked well, and in other cases it's one of those things that was, they tried to integrate it. The cases that worked, the one that comes to mind is the this hammer drill that just pounded a heating element into the ice, through the debris and into the ice. So there wasn't anything to rotate. And the heating element was at the very tip of their probe, if you will, and it worked well. They had to make sure that this probe would stand up to the hammering that it was put through, and then they had to have a way of actually extracting the water that they were melting once that probe was hammered into the ice itself. Other teams have used these earth augers, and there are some that have used ice augers, both of which had some sort of heating element, or teams have added heating elements to the augers themselves. Some of them had problems with those breaking off or failing while they were drilling. Other teams separated the two functions. They had an auger or a drill, ice drill, if you will, that created the hole. And once they got into the ice itself, they had a separate device that they withdrew the auger, cleared it from the hole, and then lowered this separate device with a heating element on the end of it into the hole, and that's what melted the ice and withdrew the ice. And there were other teams still that had combinations where they did not try and melt anything below ground. They used their auger or ice drill to bring ice chips up from below surface and then put them in a separate heating container, and turn the ice chips into water, and then the water was delivered from there to the external collecting device. So there are different combinations that you can use that involve putting the heating element below ground, keeping the heating element above ground, integrating the heating element with your auger, or having it as a separate device from your auger. All those I have seen those all tried, and all with varying degrees of success or challenges depending upon the particular design.
We have another question from the chat. Stacy, you might be able to answer. What would be the worst case scenario that you would recommend us preparing for? Should we test on concrete blocks? Stacy, you may be muted.
I think you're looking for an answer that we probably can't provide you with. We've provided a list of all of the different types of materials that you may encounter. So looking at that list, which includes, there you go, thank you, dry sand, clay mixed with 20% sand and maybe 10% gravel. When we say gravel, we're talking about like your typical drainage rock that you could buy at Lowe's or Home Depot's. You could potentially see clay that's mixed with just the 20% sand and no gravel. There could be clay mixed with some larger rocky inclusions, and solid or consolidated rock or stone. And what we're talking about there is basically, if we do decide to use that layer, it would be in a slab format. So it wouldn't be just a bunch of rocks compressed together. It would actually be a slab format. There's also the potential for aerated concrete or crushed cinder block. But unfortunately, that's all the information that we can provide to you guys today. Well, that's all the information we can provide, period.
Any other questions, Tori? We should.
Let me answer or add to what Stacy just said, I think, without giving anything else away. I think that if I understand the questioner, if you can't handle something that's on that list, you should probably, it's worthwhile making sure that whatever device you come up with can handle everything on that list, because anything on that list could be there. And if you decide that, well, you're going to take your chances on not being able to drill through one of them, that's probably the one you're going to find that's in the actual competition. There may be another way to interpret the question. Do you have to have a single device that can do all of those? That would be probably the optimal solution, is to come up with one way of getting through all of them. But you don't have to have one device that can get through all of them. If you find that you have a couple of different, if you have one device that can get through some of those types of materials, but not others, and you have a separate device that can get through the ones, the balance of the ones that are on that list, that may be the design that you want to follow up on. Just remember that you have to come in under the mass limits that are set for the competition. So you can't have one device for each of the layers, I guess. It would be the one way of handling all of that. But you don't have to have one mechanism that gets through all of those layers. You can have different devices. Just account for that in how you operate your machine, and the mass limit that you're faced with is part of the competition rules.
And thanks. I think I'd like to add a little bit on top of that we are providing the information that the hardest layer is going to have an unconfined compressive strength of around 25 MPa. So that's going to be the hardest material that you'll encounter, if that's helpful.
We haven't received any other questions from
I would like just to add one thing. I mean, this is ultimately about trying to enable drilling into ice at Mars. And just to emphasize how cool that challenge is, we have no clue about what you're going to be drilling through there. And when you get down into the ice, that ice has been frozen for billions of years. It is like solid concrete, and so, keep that in mind too. This is partly about trying to figure that problem out, and, and build, kind of have that in mind designing this. That's actually the cool part.
And I guess just to cover these last, in the little time we have left, the last couple of points we wanted to get to. As the teams raised, for those of you out there watching who are worried about running the competition at your school and making sure you're prepared come actually getting to Langley, these lessons learned are available on the website, so feel free to read through them in more detail. But like Rick mentioned earlier, a big point for us is that it's meant to be a collaborative exercise. We want, you know, everyone to learn from each other's mistakes and each other's successes. And to that end, we're using Slack this year for all of the 10 finalist teams. We'll have a community forum to discuss what is and is not working for them. And in terms of, you know, stuff to keep in mind when running your own team at your own school, folks reported that, you know, some of them had teams of 20 people, and that was really difficult to manage and may not have been the best solution. Others, you know, meeting regularly is very important. You know, establishing, you know, roles and responsibilities is very important. And go in each week, you know, knowing what you're trying to accomplish and what you want to get out of it, because you need to have that integrated testing done before you get to the competition. I can't emphasize enough how important that is to making sure that you get the run that you want at the actual competition out of your drill. Just you know, kind of closing out on the post-competition side, we're going to be collecting your lessons learned too, because we want to know what you know, how did you take this information? You know, what was useful, what wasn't, and so keep that in mind as you're going through. You know, you're part of the scientific process that is discovering the best way to drill through regolith and access subsurface ice, and you need to keep good data to be part of that. And so we want to see your results and see your process so that we can pass it on and do this on Mars. And I'll turn it over to Rick if you have any closing statements.
No, I just don't underestimate your ability to contribute. And this is not going to be done by one agency, many agencies, or one company, or whatever. We need a lot of ideas from a lot of different places, and this is a very important area that actually helps determine where we set up a base. And we're really looking forward to seeing your ideas, and most importantly, we thank you for joining the competition.
All right, well, that wraps up today's Moon to Mars Ice and Prospecting Challenge briefing. And Rick, Bob, and Steve, we'd just like to really thank you for taking the time to go into detail about some of those lessons learned. For those of you that are watching, we really hope that you take those lessons learned to heart and they help you as you design your next concepts. So we're really looking forward to seeing those. Just a few little tiny housekeeping things. If you have any future questions, we want to be here for you. We are here for you. So the mechanism for doing that is to continue to email us your questions at rascal@nianet.org. That email address is all over the website. We will respond to you directly, and then we'll make sure that we also post the answer on our FAQs page so that everybody has equal access to all of the questions and answers. So definitely go back and check that FAQs page very frequently. A reminder that your project plans are due at 11:59 p.m. That's Eastern time on Thursday, November the 15th. So make sure to get those in by that deadline, and we just can't wait to see what you guys come up with. Thank you all for being a part of this today, and know that this we've actually recorded this session, and it will be posted on the resources page of the website. So if you ever want to go back and reference anything again, it will be there for you. Thank you guys. Have a great day.